Good morning, everybody, or good whatever part of the day it may be in the part of the world that you're tuning in from. My name is Irfan Durmic. I'm originally from Sarajevo, Bosnia and Herzegovina, but I'm currently studying mathematics, physics, and German at Williams College. Now, maybe you have like an instinctive impulse to say that I'm insane, but my kind of personal belief is that all of us scientists slash researchers slash STEM people are at least a little bit crazy. And that's kind of like my mantra when it comes to science. And there's like a very interesting characteristic thing about science that I strongly believe in. Our goal in science is to find these beautiful patterns in the universe and the world and to somehow find the connections between them. And I'm going to use this opportunity to quote unquote quote Einstein, because nowadays you don't know what Einstein actually did or didn't say. Einstein had this habit apparently of saying that if you encounter a problem that you can't solve, the best way to solve it is to switch from one paradigm to another. And that's kind of going to be our goal for this talk today. So we'll be talking about parallel diffusion on complete graphs, and we're going to try to connect complete graphs to polyominoes, so two mathematical objects. So here's first a quick overview of the talk. Obviously, not everybody is an expert on graph theory. I don't personally consider myself yet to be one, but we're first going to do a quick overview of graph theory, after which we will talk about what is actually a polyomino, and we will encounter a very specific family of polyominoes, the so-called Bord pile n-ominoes. We'll talk about them a little bit later. We will notice a very interesting connection between complete graphs and Bord pile n-ominoes, and we will try to do a sketch of a proof for the specific bijection that we're building. The proof is a little bit more involved, and we would need significantly more time than we have for this talk. So my goal today will just be to give you a little bit of a sketch on how to do the proof. Furthermore, we will work on applying the results of this proof of this bijection. We're going to talk about some further avenues of research. I'll tell you a little bit about the stuff that I've been doing. And of course, I got to acknowledge the people who've supported me over throughout this talk and this whole research process. So let's begin. Here's a little anecdote. I had a chemistry professor in high school who loved to say there isn't anything nicer in life than an example. And I'm going to up that a little bit because we're, now fancy college mathematicians. There isn't anything nicer in life than a definition. So let's start off with the definition of a graph. And I'm going to use this opportunity that we're all virtual to do this. So a graph G is a set of vertices, which you can define as some set V of G, and a set of edges between vertices, which is denoted as the edge set E of G. Now, I like pictures, not the best one at it. If I was, I wouldn't be a math major, I'd be an art major. So let's try to see, can we notice graphs in the real world? Or are graphs just these abstract, weird things from mathematics? So let's start off with something typical. I see a house right in front of me through the window, so let's start off with a house. So here's a little bit of a house. We're going to pretend it's a house for all intents and purposes. And that's our little house. And what do we notice in this house? I'm going to change my color. You'll notice that this house has different vertices. So it satisfies this part of the definition, but it also has these edges, these connections between the vertices. It has this edge set. So a house is actually a graph. And we can talk about more specific things when it comes to graphs, the different subfamilies and whatever. But the thing that is interesting for us right now is we're going to define what a finite graph is. A finite graph is simply put a graph that has a finite number of vertices and a finite number of edges. So this house would represent a finite graph. Furthermore, we're going to introduce the concept of a simple graph. A simple graph is, no pun intended, simply put, a graph that doesn't have any sort of loops. We're just talking about these lines, these simple connections that even a person like I can draw. And now we're going to introduce this concept of a finite simple graph. So a finite simple graph is just a graph that is finite and simple. And we're going to be talking about all the graphs that we introduce in today's talk. They're going to be finite simple graphs. And finally, we can introduce one part of the title of today's talk, a complete graph. So complete graph on n vertices is denoted by k sub n. And it is a simple graph in which all of the vertices are connected via edges. So here's a little bit of an example. Here's a triangle. A triangle is a graph, and it has three vertices. One vertex, another vertex, and another vertex, and all these vertices are connected via edges. So this is a complete graph. But let's look at a square. So we have a square over here, or this is more of a rectangle, I guess, and it has four vertices. The vertices are not all connected. They become fully connected when we introduce diagonal lines. So to make this graph complete, we just introduce the diagonal lines. So the big idea behind a complete graph is if you start off from any vertex So let's say I start off from here. I have different lines that can bring me to any other vertex. So that's a little bit of the story of these, of the basics of graph theory. Here are a couple of nice pictures and nice different representations of the characteristic complete graphs, K3, K4, K5, so on 3 vertices, 4 vertices, and 5 vertices. And for the purposes of this talk, we'll be working on K5, mostly because I think it's kind of an interesting and fun example. We could have done, any one of them, but this one is the easiest to work with and easiest to draw. And I noticed that like already half of the audience is falling asleep, so again, I'm going to use the good old trick of Zoom. Let's play a little game. Here's the so-called chip firing game. This isn't exactly, the link that I just sent to the chat isn't exactly the thing that we'll be playing around with, but you can play with that if you get super sleepy and super bored. So, let's play a little bit of a game on these chips, and now we're going to technically introduce parallel diffusion, and I like to call parallel diffusion the Robin Hood protocol. That's also how I'm calling it in my little paper that I'm working on. So let's first look at what we have here. We have some sort of a configuration. This thing over here is the C naught initial configuration, and I'm going to denote this as over here. So initial configuration. And you can imagine this just as some sort of a distribution of chips, these different stack sizes. So these numbers above these vertices represent some sort of like chips placed in a vertex. For all the modern kids, you can imagine it as different, Bitcoin in a specific vertex or whatever. And this is some sort of an initial configuration at time is equal to 0. You can imagine this as some sort of a process that's happening over time. And now we're like, okay, I want to play around with this Robin Hood protocol. And what did Robin Hood do? He stole from the rich and gave it to the poor. So let's focus on these quote-unquote rich vertices. Here's one rich vertex, V2, and here's another rich vertex, V4. And now we're also going to try to make Bernie Sanders happy by moving along these different chips, these different stack sizes, changing them around. So V2 realizes, oh, V1 has less chips than I do, so he moves along from a chip from V2 to V1. Another chip moves from V2 to V3 because V3 has a smaller stack size, a smaller number of chips than V2 does. And we repeat the process with V4. So what do you notice here? You notice that V5 just got a chip from V4. So now our total stack size here is 2. V4 sent 2 chips along, so we have a stack size of 1. V3 accepted 2 chips, so it went from 0 to 2. V2 gave up 2 chips, so now only has 2 chips, and V1 accepted a chip, so now it has 1. So what do we just do? This isn't the same configuration anymore because we have a different distribution of chips. So we move from configuration C0 to configuration C1. And this configuration C0 actually has a very specific name that we'll reference later in our proof. It's called a pre-period configuration. And you will notice why pre-period very quickly. So notice this configuration C1. So we go from configuration C1, we get configuration C2, but look at configuration C3. It's exactly the same one as C1. So C1 and C3 are the same configuration, and C2 and C4 are the same configuration. And if you kept on going, you would end up in an endless loop. So this whole set of configurations are denoted as period configurations. Period configurations. In these different period configurations, based on previous research, we know that at most the period length, i.e. the number of configurations you have to go through before you have a repetition, is either 1 or 2. That's from some previous work. But we don't know anything about these pre-period configurations. Now, let's move on to a little bit of a more trickier situation. Let's see how we play this chip firing game on a complete graph. So what am I doing here? So I move, okay. First, let's introduce the notation here. C here represents the period configuration, but it's a little bit more specific. So this 3 represents that we have one vertex of stack size 3. This 4 represents that we have 2 vertices of stack size 4, and the 5 to the 2 represents that we have 2 vertices of stack size 5. So far, so good. And now I'm applying this Robin Hood protocol. So 5 has to send a chip here, has to send a chip here, has to send a chip here. Now this 5 has to send a chip here, has to send a chip here, has to send a chip here. This 4 has to send a chip to 3, and this 4 has to send another chip to 3. This is really difficult to follow. So I'm just going to say this is really messy. And like the true mathematician, I'm going to give up on this and work on another problem to, like, get some divine inspiration. So let's talk about polyominoes. And I'm a 90s kid. I was born in 99, so I want to count as like an honorable 90s kid. So here's a little bit of a Tetris game. Again, who got bored with the chip firing? Here's some Tetris. What is a polyomino? Again, definition. A polyomino is a plane figure composed of a number of connected unit squares joined edge on edge. And a polyomino with exactly n unit squares is called an n-omino. So here's an example of an n-omino. Here are a couple of unit squares. And they all have to be connected edge on edge. So you have to be able to, if you start from one unit square, you have to be able to come to all the other unit squares, any direction that you decide to follow. So what do we see? How many unit squares do we have here? 1, 2, 3, 4, 5, 6. So this is a 6-omino. And now we're going to define something else, which becomes important later on. In a polyomino X, so usually we denote polyominoes as X, just like we tend to denote graphs as like some sort of a G. Is a horizontal. So in a polyomino X, a horizontal strip, or a so-called H strip, represents the maximal rectangle of height 1. Don't think about it too much right now. We'll get to a nicer picture that elaborates this. But this is a little bit of a more important detail. So the infinite area enclosed between the lines y is equal to k and y is equal to k plus 1 represents a row. So we formally defined a row. We know, like, from intuition what a row is, but now we're like, oh wait, let's imagine putting this in a coordinate system. Here's the line y is equal to k and y is equal to k plus 1. This is going to be a row. And now let's introduce another picture. But before we formally introduce this picture below, we're going to mention what is a board pile polyomino. So board pile polyomino is a polyomino which has at most one H strip. So what does that mean? That means it can have 0 H strips or 1 H strip, which is something we use later. And a board pile polyomino with n unit squares is called a board pile n-omino. So let's look at our notation again here. So this is our notation, and we have a specific labeling convention. We have to define a couple of things here. So D1, by convention, is defined to be 0. And SI, these different SIs represent the order of the H strip. But when we take the cardinality of those SIs, they represent the number of unit squares within that specific H strip. Or in the case of this picture, they're basically just telling us, oh, how many unit squares do we have in a row? So it makes it a little bit simpler. Now, you might be wondering, what are these DIs, D1s, D2, and whatnot? Each DI represents the distance between the maximum x-coordinate of some H strip SI and the minimal x-coordinate of some H strip that comes before it. So SI minus 1. In order to motivate this, we're just going to work through this little example. So what do we notice? X is equal to, we have these ordered tuplets. So we have, by definition, D1 is equal to 0. And this first row has just 0 unit squares, so that's 0. The next one, we notice the maximal x-coordinate is free, and the minimal x-coordinate in the previous row is 0. So we have a free. Then we have 1 unit square, 1. And then we notice the following. So we have the maximal x-coordinate is free, and the minimal x-coordinate is 2. So we have a 1 here. And we have 2 unit squares in this row over here. That's 2. And similarly, it applies to S4. So it's 1, 2. So far, so good. And now this is the moment of divine inspiration. Let us imagine that there is some sort of a mapping that we can create from board pile n-ominoes, X, to complete graphs, to configurations on complete graphs, so some C. So we can apply this function, and this is, going through a bunch of different examples, you could get to this idea at this point of how to make this work out. And let's see, can we apply this idea from Einstein? Because we know a lot of stuff about polyominoes, so we want to double check. Is it possible for us to go from board pile n-ominoes to complete graphs? Also, just to double check real quick with the host, if I go a minute or two over, is that okay because of our delay in technology? Okay, perfect, thank you. Just so I know how much to time myself here. Okay, so let's check, does this mapping actually work for the example that we've created? So let us again remember, how do we define X? So our polyomino was 0, 0, 3, 1, 1, 2, and another 1, 2. And let's see, can we apply this mapping that we mentioned? So you can notice this mapping over here. So we're applying this function f to our board pile n-omino X that we defined. And let's write this out. So we have some 0 to the 0. That means we're going to have 0 vertices with a stack size of 0. And now we're summing up over all of the previous di's. Remember, these over here are the di's. So we have 0 plus 3 to the 1. And then we sum up again. We have 0 plus 3 plus 1 to the 2. And then we finally have 0 plus 3 plus 1 plus 1, 2. And let's write this out. The 0 to the 0, we can kind of sort of ignore that because it's just saying, oh, we don't have any vertices with a stack size of 0. So who cares about that? But we do have one vertex with stack size of 3. We have 2 vertices with a stack size of 4. And we have 2 vertices with a stack size of 5. This looks kind of familiar. This is exactly the configuration that we talked about when we were looking at the complete graphs. And now we're going to just state this theorem and the bijection and give a little bit of a sketch for the proof. So for all n greater than or equal to 1, there exists a bijection between the set of all board polyominoes, that is exactly this function f, and the set of all period configurations on unlabeled complete graphs. Now this proof is a little bit tricky, so I'm just going to walk you through very quickly through the basic ideas. There's this important lemma that tells us let x be some sort of a board polyomino with exactly n h strips. We know that some number I is between 1 and n minus 1, meaning the number of h strips, and then the di's plus 1 will follow the specific relationship. And then when we actually delve into the proof, there are a couple of little steps and little tricks that we have to follow along. So first of all, since we're talking about a bijection, this is actually a theorem that goes in 2 directions. So we're going to split it up in 2 parts. First, we're going to prove that it works from the board polyominoes to the different period configurations, and then we're going to go from the different period configurations to board polyominoes. If you're wondering, that is exactly how I built this example that we just worked through. I first decided, oh, I'm going to work with K5, made a little bit of a graph, added some chips, and then I decided how to switch back from the K5 to a board pile n omino, specifically a board pile 5 omino. A cool result that we need here in doing this proof is that if you change the stack size of a configuration by an integer number, meaning that you subtract or you add chips to the different vertices of an unlabeled complete graph, the whole process doesn't change. And then finally, you're going to use an inductive approach here. The important corollary that follows from this is that basically the number of period configurations on an unlabeled complete graph on n vertices follows this recurrence relation presented over here if n is greater than or equal to 5. That is really cool because it gives us an opportunity just to look up some information about a specific board polyomino on the online encyclopedia of integer sequences. And if you look it up, how many different board polyominoes you can have on n is equal to 5, you will notice it's 61 of them. And that tells us that the different period configurations on complete graphs are also equal to 61. And trust me, I actually did write them all through for this example. It took me 4 hours, so bad idea. Yeah, so just, if you don't mind, if I can add just like a quick second. There's another, we can do this for label complete graphs. There are a couple of open problems. It's possible to think about how to generalize this. And there's still the issue of period configurations. And I just want to take a quick second and thank the conference for inviting me, for moving me from the wait list to the actual speakers list. I want to reference this paper by Mullen, Novakovsky, and Cox, and I'm going to send that over here. And I also want to thank Professor Pamela Harris for being my mentor through this. And if anybody has any questions, let me know.